is on estimating with finite and infinite sums. So we're probably not going to get to the infinite sums today, but we're going to do the finite sums today. So we're going to take it way back to Algebra 2 when we talk about sigma. Sigma stands for sum, right?
Yes, ma'am.
So if you remember, we did things like this, like the first example, write the following in expanded form in Algebra 2. So if I have the sigma, so the sum from I equals 0 to 5, what that means is I'm going to plug in 0 for I, then 1 for I, then 2 for I, 3, 4, and stop at 5. And I'm going to sum them. Sigma means sum and not multiply all together.
So do you plug in 5 or not?
Yes, I do plug in 5.
Okay, your answer is 36.
So I'm going to have 2 times 1. It is 36. Good job. He pulled a little Gauss trick on there, didn't you?
Did I?
I don't know, probably.
I don't know.
Now, you don't have to write all of this out.
Wait, Miss Klaus, is that 2 times 0?
Yes. So I'm plugging in 0, I'm plugging in 1, I'm plugging in 2, all the way to 5, and I take all of those answers and I add them together. So when I have all those answers, it's 1 plus 3 plus 5 plus 7 plus 9 plus 11.
I didn't even pull a trick. I just added them in my head.
You just added them together. So what I was saying is Ian could have done the Gauss trick. Do you guys remember the Gauss trick?
No.
When you have an arithmetic sum or arithmetic sequence. So we have 12 plus 12 plus 12, which is a total of 36. Do you guys remember that trick?
Wait, what?
Or you have the meat,
Guys.
the meat, which would be 6, and you multiply by 6.
It's okay. All right, here we go. So number 2. So number 2 is different. Okay, it's not an arithmetic sequence. It's not going to be like 1 plus 2 plus 3 plus 4. It's not that. Shh, guys, quit interrupting. Just listen. Pay attention. All right, so if I have k equals 1, and I'm going to go 2, 3, 4, 5, all the way to n. Okay, n is, we don't know. We're eventually going to get to where n goes to infinity. Okay, so with this, I'm going to have 1 over n times 1 squared plus 1, 1 over n times 2 squared plus 1, plus 1 over n times 3 squared plus 1. And I continue this pattern all the way to 1 over n times n squared plus 1. So with series notation, summation notation, we can sometimes like rearrange our terms and pull things out. Okay, do we have a GCF for all of these different things? What's in common to all of them? Yeah, the 1 over n. Do you guys see 1 over n, 1 over n, 1 over n? So we can pull a 1 over n out. Then we just have 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, and so on. So what we're going to do is we're going to rewrite it, and we're going to say, oh, well, I have 1 squared plus 2 squared plus 3 squared all the way to n squared. And then I have 1 plus 1 plus 1. How many times do I have 1s? N times. So if you wanted to write this in a simpler way, it would be 1 over n times the summation of I squared, which we'll just write as 1 squared plus 2 squared plus n squared, plus n. And there's lots of things that you can do with this to make it even simpler. So there are summation formulas. So I told you in Algebra 2 about Carl Friedrich Gauss. He was a famous mathematician. Riemann actually studied under him. He was Riemann's teacher eventually. Riemann is the guy that does rectangles, right rectangular, left rectangular. So when Carl was 10 years old, the teacher assigned the task of finding the sum of the numbers 1 through 10. It's rumored that she wanted half an hour of peace and quiet, or other stories say that he got in trouble. Do you guys remember this whole story? Yeah. Mm-hmm. 1 through 100, yeah. That 1 through 10 would be really easy. So Carl quickly found the sum, much to his teacher's annoyance. So do you see how he found the sum? Do you guys remember? It's like that little rainbow method.
You find the...
Add the first and last. So you had 101. So we have all these pairs of 101. So 50 pairs of 101. So 50 times 100 plus 1 is going to be 5,050. Easy, right? So he did it right away and was like, oh, the answer's 5,050. And she was like, no way, the answer's definitely not 5,050. And sure enough, it was. So he ended up being a famous mathematician, did lots and lots of things in the math world.
Yeah, Frederick.
Yeah, His name's not Frederick.
Can you go back?
Friedrich. Carl Friedrich. You don't need to write down all of these things. We've done this before. All right, so there are 4 different summation formulas. 2 of them super simple. 2 of them I will give to you if you ever need them. All right, so the first 2. So if I have a sigma and then I have 5 in it, like if I had this, sigma, 5, and I said start at I equals 1 and go to 100. How many times would I write 5? 5 plus 5 plus 5 plus 5 plus 5. I'd write it out 100 times, right? So what would my sum be? 500. You guys all figured that out. No big deal. That's what this one is. So if we have a constant, then our sum ends up being C times N. So 5 times 100 was 500. So C is some kind of constant. If I was summing up 5 plus 5 plus 5 plus 5, that's that example. The next one is the Gauss formula. So if I had 1, the summation of I, that's 1 plus 2 plus 3 all the way to N. So what do? We add the first and the last. So 1 plus N. And then we multiply by the number of pairs. We have N divided by 2 pairs. Do you guys see where that formula comes from? You got it? Same thing. N times N plus 1 all over 2. It's the Gauss formula. All right, and then the next one, I squared, I'll give to you. So it's N times N plus 1 times 2N plus 1, and then all over 6. And then I cubed I'll also give to you. Okay, usually we use the I squared, not the I cubed. Sometimes we'll use I cubed, though. All right, so we're going to use the summation formula to find the sum. Now this first one only goes from I equals 1 to 10. Could you easily write it out and be like 1 squared minus 1, 2 squared minus 1, all the way to 10 squared minus 1? Yeah. What if it was 1,000? Not so much, right? Yeah. So we have a reason that we do this, especially for I equals, like if I go from I equals 1 to N, and N goes to infinity, right? We need some way to do this. Okay, so we use these summation formulas. So think about what this represents. You don't have to write this down, but it's 1 squared minus 1, 2 squared minus 1, and so on, all the way to N squared minus 1. So really, I can kind of distribute, I'm using that lightly, a sigma. Like I can say, oh, it's a summation of I squared, and then I have all those minus 1s. Minus 1, minus 1, minus 1. So I'm going to do minus 1 in a sigma as well. You can see how that works? It's like moving things around. It's like writing all of these together and then writing all of these together. This was the red one. That was the green one. You see it? All right, so if I have the summation from I equals 1 to 10 of I squared, that's using the formula up at the top. So if I have the summation of I squared, it is N times N plus 1 times 2N plus 1 all over 6. What's N in this case? 10, right? So I'm going to do 10 times 10 plus 1 times 20 plus 1 all over 6.
Equals minus 10.
Yeah, and what's the next one? Well, it's 1 added to itself 10 times. 1 plus 1 plus 1 plus 1. 10 times. So what do I get? 10. That was from the other formula, the summation of C.
Equals 300.
That was from this one. Ian, give me a second. You're correct, but give me a second. All right, so we do 10 times 11 times 21 all over 6. And I would recommend, you know, if you didn't have your calculator, you can simplify. You can say, oh, 21 and 6 are both divisible by 3, so I get 7 and I get 2. 10 and 2 are both divisible by 5, or not by 5, by 2, so I get 5 and 1. So I have 77 times 5, right, minus 10, and you can find it. So you get 385 minus 10 is 375. Yeah, Jordan?
Where did minus 10 times 1 come from?
It came from the green part.
Oh, okay.
Maybe I should do that. Color code. It's what? Yes, do they color code? I was setting the trend way before Khan Academy. All right, so I equals 1 to 100. So I have 3I squared plus 3 all over 100. So again, think about how you're rearranging this, how you're pulling it apart. So the first thing that I'm going to do is I'm going to bring the 100 into both pieces. So I'm going to say, okay, this was the summation from I equals 1 to 100. Oops. Of 3I squared over 100 plus the summation of 3 over 100. And our goal is to kind of get it in one of these 4 forms. To break it apart so we can see what the sum is going to be. So imagine writing this part out right here. Don't write it, but look up here. So if I have 3i squared times 100, isn't that 3 times 1 squared over 100 plus 3 times 2 squared over 100? What do they all have in common? 3 over 100. Can we pull that outside of the sum? Yep, it's just the distributive property. That's all it is. So I'm going to have 3 over 100. I factored out a GCF, basically. And then I have the summation of I squared going from I equals 1 to 100. And then same thing here. I could pull out the 3 over 100, but be careful. You still need to do that summation. What's the summation of? 1. If I pull out that 3 over 100, or you could leave the 3 over 100 in, and that's now your constant. Either way. So I'm going to get 3 over 100 times, my formula is n times n plus 1 times 2n plus 1 all over 6. And the next one's going to be my 3 over 100 times what? 100. You guys see it? The summation of 1 100 times. If I add 1 to itself 100 times, 100. Yes, Julia is correct. That is just 3. Amazing.
Okay, thanks for killing that.
All right, so you can also reduce out some other things before you actually put it into your calculator or anything. So you have 101 times 201 divided by 2 plus 3. What do you get? 10,000 something.
10,153.5.
Yep. All right, so we get that. All right, so there is a way to do this in the calculator, but that's not the whole point of like doing this with calculus, because like I said, calculus, we're going to go to where we have n on the top, right? And then we're going to take the limit as n goes to infinity. So I'm going to show you how to do this in your calculator. I always forget how to do this on my own calculator. Like, I'm a math teacher. I do this once a year. I don't really use the summation of a sequence very often, but I will show you. So go ahead and get your calculator out, and I'll show you what you will put in. I think I wrote it up here too, because I always have to hunt around every single year, and I'm like, oh, how do I do this again? All right, so here's what we're going to do. We're going to do second. Are you guys paying attention? All right, this is not just you guys sit back in your chairs and talk. So I'm going to do second list. I'm going to go over to math, and I'm going to do the sum. So hit enter, and it gives us sum and then a parenthesis. List, I'm doing it up here on the screen, guys. It's the stat button. It's over by the cursor. All right, then I'm going to go back in there. So I'm going to do, again, second list, so it's the stat button. I go over to operations, ops, and I go down to sequence, because I'm finding the sum of a sequence. Okay, now mine shows up as sum sequence parenthesis. Yours probably doesn't, because it's a newer calculator.
Wait,
If yours doesn't, it's okay. I'll show you what's back.
table of stuff with this?
That's what I'm telling you right now. So mine shows up as sum, sequence, and then parentheses. So what I would do is I would put in the function, and that's what I put in here. So then put in function, comma, x, comma, a to b to 1. Okay, so I'm going to do, my function for the first one was I squared minus 1, so I'm going to do x squared minus 1. And that's what goes in for function for you guys. So x squared minus 1. Well, what's the first line?
EXPR.
Expression. Yeah, put in that for expression.
Exactly.
All right, and then it says variable, x, comma. So we put an x for yours. Don't put a comma, just put x. And then we're going to go from the bottom number to the top number. So we're going to say 1, comma, 10, comma. And we want it to go up by steps of 1. So like go from 1 to 2 to 3 to 4. We're stepping up by 1, so we do another comma, 1.
Wait, isn't it 100?
I'm doing the first one.
Oh, never mind.
And then I hit enter, so I got 375. Okay, so one more time. If I'm doing this, let me use the other calculator, see if it shows up the way yours does. So I'm going to do second list. Go over to ops. No, wait, math. What was it? See, this is where math. Go down to sum. See, that's why I always have to search around. I'm like, oh, I know it's sum of a sequence, but I have to find sum and sequence sometimes. Operations. Sequence, number 5. I put in, so in this case, I'm going to have 3x squared in parentheses plus 3. So my whole numerator in parentheses divided by 100, comma, x, comma, 1, comma, 100. Go up in steps of 1, so comma 1. Enter. It thinks for a little bit. 10,153.5. So you can use that to check your homework. Do not use it to do your homework.
Wait, is that where we put like start and end?
Yeah, so the start is 1, the end is 100.
What should we put in
X.
The variable is x, yeah. Sorry, mine doesn't show up the same way yours does. So yours will say like step is 1. It's all the same numbers here. Like they're the same, it's the same order on your calculator. It just says like expression instead of function. So expression x, bottom number to top number, comma 1.
So
All right.
why does our answer say 375 but the calculator says 395?
My calculator said 375, so
Mine said 375.
Mine says 395.
I don't know, guys. You put something in wrong. So I'll check it in a sec.
Oh, that's a plus one.
Yeah, don't do +1, -1. All right, so Archimedes, you've heard about Archimedes before, right? Do you guys know what he's famous for saying while running naked down the street? He ran naked down the street screaming, "Eureka, Eureka!" That's your history fact of the day. Yeah, because he figured out that someone was cheating the king from gold in his crown by stealing the gold and replacing it with other metals. While he was in the bathtub, he figured it out. All right, so anyway, he also approximated pi using what we call an exhaustion method. So here's what he did. I'll quickly draw a little sketch. He drew a hexagon with a circle inscribed around it, and then he drew a hexagon with a circle inscribed about it. Oh, this is not going well. And he found the perimeter of each of those hexagons if they had a radius of 1, and then he used it to approximate pi. So he kept using bigger and bigger, like a hexagon, and then an octagon, and then a decagon, and so on, dodecagon, to find it. All right, anyway, so we can do an exhaustion method with calculus as well, and we've done this before, so this should not be very hard at all. And you're actually going to have this, but most of your homework is on, okay? So if you have a curve, y equals x squared, and you want to find the area from 0 to 2. This is our region S that we're finding. So the area trapped by the curve from 0 to 2. So how would you try to estimate the area? So you could do different things. You could try triangles. You could break it into like little squares. You could do lots of different things. Do you guys remember what we used before? Yeah, we used rectangles. So that's what it says in this next one. It says divide it into strips. So if we take our y equals x squared, and we go from, oops, that was a weird line. And we go from 0 to 2, we break it into 4 strips. Oh, this is tiny. Should have used my previous sketch. I'm going to use the other one. It's bigger.
How many should we have?
You should have 4 strips,
Why 4?
because that's what I told you to use. Okay?
Is each 1/2?
Yeah. So 1/2, 1, 3/2, 2. That's what it says in the instructions here. Suppose we take our region S and we divide it into 4 strips. Okay, and we use these vertical lines, x equals 1/2, 1, 3 over 2, and 2. So find the area of each rectangle using right endpoints. So whenever I say right endpoints, a lot of people mess this up. We're taking the endpoint on the right-hand side as the height of that strip. Okay, so we're creating these rectangles using the right side as our height. I realize that when you draw the line, you go towards the left. Don't be confused about that. Right? It's the right side is the height. And we want to find the area of each of those rectangles. So in order to do that, we need the height of each of those rectangles. So we use our original function, which in this case was easy. It was just x squared, to find the height. Okay, so if I started with the left endpoint, this first left endpoint would be a height of 0, right? What's this one right here? Let me draw it in red. This one right there. What height is that? 1/4. How did you get 1/4, Emerson? Yeah, we did 1/2 squared. How about the next one? 1. 1 squared is 1. How about the next one? 9/4, right? 3/2 squared is 9/4. And the last one is 4. So I'm plugging in so we're plugging in the x value. Plug in x to y. Y equals x squared. So I talk about the area of each of those. My area of the first rectangle, this one right here, is going to be a width of 1/2 times a height of 1/4. And then the next one is going to be a width of 1/2 times a height of 1. And the next one's going to be a width of 1/2 times a height of 9/4. And the last one's going to be a width of 1/2 times a height of 4. Okay, we call this R4, right hand rectangles with 4 rectangles. Okay, you might also see right rectangular area method. I feel like that's a lot to write. I just write R4. So you might see right rectangular area method with 4. All right, so the easiest thing to do is pull out the 1/2 and just add in 1/4, 1, 9/4, and 4. So 10/4, 5/2, 5/2 plus 5 is 10/2, so 15/2 times 1/2. Ian, is that correct?
Yeah, 15/4.
Yeah, so our answer is 15/4. All right, so what if we wanted to do a left-hand approximation? So it's the same thing.
We would use 4.
We're still going to use 4,
Hold on.
All the height be the same.
kind of.
Mrs. Cox,
What?
how did you go once you had the width and the height?
I found the width and the height for each rectangle, and I added them all together.
You add all the widths and all the heights?
Width times height, width times height. So the area of each rectangle.
I did that and I didn't get what you used.
Yeah, did you do the 1/2 at the end?
Those are all 1/2.
I pulled the 1/2 out. So then I did 1/4 plus 1 plus 9/4 plus 4.
Oh, I was doing it by the x value there. That's why I got.
Oh yeah, the width of each rectangle is 1/2.
Oops.
Yeah, so how about this one? So if I'm talking about the heights for each of these, now the first height is 0, and the next height is 1/4, and the next height is 1, and the last height is 9/4. I'm not using 4, am I? Do you guys see it? So my left-hand approximation with 4 rectangles is going to be 1/2 times 0 plus 1/2 times 1/4 plus 1/2 times 1 plus 1/2 times 9/4. So what do we get, Ian? Oh, man.
I'm sorry.
Over 2.
14
7/2. I think it's 7/4. Yeah, 7/4. So if I wanted to get an even more precise over us or an area, so what I could do is I could find the average of those two, right? I could also find more rectangles. So our goal is eventually we're going to take a number, like we're going to go to an infinite number of rectangles. So we're going to do all this summation stuff with an infinite number of rectangles.
Oh.
All right, let me pass out your homework.
So ready?